Okay, let's look at briefly the energy balance. I think most of you are probably already aware of it. I use this figure stolen from the internet, somebody's stock figure, I'm sure. Apologies. So sunlight coming in is obviously in the visible band. That's where most of its energy is reaching the earth. So you can think of the stove with this fire which is visible. So that's in the short wave, which we have evolved to see in. And the pot is getting heated. You cannot see that it's hot, but obviously if you go near, it's going to burn you, right? So it's putting heat into whatever material that's in it, and Earth is like this. It's receiving solar energy in certain wavelengths which are visible to us. Everything is getting heated, and the energy that is going back to space is in the long wave, just like this pot which is emitting heat in the wavelengths that we cannot see. So here is the solar radiation spectrum. Obviously the entire spectrum goes from gamma rays, X-rays, to infrared, to visible, to radio waves, microwaves, and so on. This is shown in nanometers. So this is the spectral radiance in watts per meter squared per nanometer, and the curve here, the Planck radiation curve, basically talks about maximum temperatures determining the wavelengths at which the energy is maximum. So that's the blackbody spectrum that we fit to it. Blackbody is anything that's a perfect emitter, so it takes all the energy it receives and then emits it unless its emissivity is less than 1. So the radiation reaching at sea level is different than what is coming at the top of the atmosphere, because you have these constituents of the atmosphere which can absorb or allow the shortwave to go in. So you can see that certain gases like H2O can be sensitive to both the short waves and long waves, whereas so this is in nanometers, and Earth's energy emission spectrum is distinctly separate from sun's energy coming in. It's in micrometers, not nanometers, and here the greenhouse gases do their work. So typically the triatomic molecules like CO2, H2O, and N2O, of course, there are also CH4 and HFCs and so on. They are sensitive to the long wave photons. They allow the short wave to come in, and the outgoing long wave can excite a bending mode or a rotational mode or a vibration mode in the molecules, which is what increases their energy, and they emit the energy out to space as well as back to the surface. So that's what gives us the greenhouse effect, right? CO2 is symmetric actually, but it has a bending mode. Typically symmetric molecules are not sensitive to the long wave. Nonetheless, the blackbody radiation of the Earth can be written as sigma T to the 4th, where T is the emission temperature, which is being emitted from some levels in the atmosphere. It's not like one particular level. Sigma is the Stefan-Boltzmann constant, so this is called the blackbody radiation or Stefan-Boltzmann equation. So what matters here is that each greenhouse gas has a particular radiative efficiency in watts per meter squared per parts per million by volume. Obviously N2O and methane are measured in parts per billion, but obviously you can also measure count them in parts per million. So the radiative forcing due to changes in their concentration can then be calculated. So we need to know the radiative efficiencies, which for CO2, methane, and N2O are respectively 0.014, 0.37, and 3.03. But these also indicate that methane and N2O are much more powerful as greenhouse gases. So that's called greenhouse warming potential. We'll come back to that a little bit later, but typically greenhouse warming potential is measured as the warming that would result over a particular period of time, like 100 years, because of a greenhouse gas with respect to CO2. So we assume CO2 is 1 as a reference, and anything that's higher has higher greenhouse warming potential, and anything that's lower has a lower greenhouse warming potential. So the concentration of the gases matters, their residence time, or how long they stay in the atmosphere, matters, and their greenhouse warming potential matters. For example, CO2 has residence times of multiple centuries. Methane has ordered 12 years, and N2O I think is a couple of 100 years. So measuring greenhouse warming potential is a bit tricky because CO2 can last for a very long time, so just measuring over 100 years is not necessarily the complete story. Keep that in mind as we go forward, but the quick balance we are looking for is what's coming in at 340 watts per meter squared at the top of the atmosphere. Earth's reflectivity or albedo on average is about 30%, so about 100 units of that 340 is being reflected and scattered as shortwave radiation. So the system is receiving 240 out of the 340. Some of it is absorbed in the atmosphere, and a lot of it makes it to the surface, and everything on the surface is warmed or evaporation is created because of that. So even though it's only receiving 240, the blanket actually ends up creating 390 watts per meter squared coming out of the surface, because there is reflection of the long wave, or the emission of long wave, to the space which has to match what's coming in, which is 240, but it's also reflecting down, so that gives us a total of 390. Imagine yourself under a blanket. The blanket is going to trap your body heat and increase the temperature, and that's its purpose, to make you feel warm by trapping the body's heat. So greenhouse gas effect is essentially doing exactly that. Okay, so enhanced greenhouse effect of 2.5 watts per meter squared is mentioned here because of human activities in terms of radiative forcing, which we will come back to. Okay, so briefly to mention, the structure of the atmosphere matters. The lower part of the atmosphere, which we call troposphere, where all of the weather happens, has temperatures warmer at the surface and decreasing to the top of the troposphere, where the temperature then changes gradient, where the ozone and absorption of UV radiation makes the stratosphere warmer. So we have a tropopause which separates the stratosphere, where ozone is formed, which is a good thing, from the troposphere, where all the weather, rainfall, convection, evaporation, precipitation, and so on happen. So obviously the atmosphere is mostly nitrogen and oxygen, but these trace amounts of greenhouse gases are critical for giving us these temperatures that are warmer. So the main thing about greenhouse effect is that the surface will be warmer because of the greenhouse effect, compared to the case where there is no atmosphere or there is no greenhouse effect. Okay, that's a key thing to remember. Just to add the details, we will see in a minute that the radiation coming in is not distributed evenly, because Earth is a sphere, and the sun's radiation that is coming in parallel to the Earth is putting more energy per unit area in low latitudes, because the area exposed is larger, compared to the curvature at higher latitudes, where the energy per unit area is smaller, but you are emitting long wave from everywhere. So it happens that at higher latitudes, beyond certain mid-latitudes, the incoming radiation is actually less than the outgoing long wave, and in the lower latitudes the solar is larger than the outgoing long wave, so you have net energy being accumulated here and net deficit of energy at higher latitudes. Obviously this is not equilibrium unless you move some energy from there to there. If you don't move, then tropics will keep getting warmer and warmer, and the poles will keep getting colder and colder. Plus, high latitudes have snow and ice, land ice, ocean, sea ice, and so on, which add to the loss of solar radiation as well. So that's the main deal about how we get weather and climate. Sun spends 6 months in one hemisphere, 6 months in another hemisphere. Ocean can absorb the energy. Land doesn't have much heat capacity. Glaciers can store the energy, but winds are required to move this energy. You also have hurricanes, typhoons, cyclones being part of this story. But ocean also moves the energy. So together the system is basically trying to move energy, and that's what gives us weather. And with global warming, we are basically changing this equator to pole temperature gradient, and that changes the winds, the evaporation, precipitation, and so on. And that's what global warming is all about, trying to figure out how we are changing the temperature distribution and the weather and climate.